Hello students, welcome to my next online class. So this is the continuous video and here we are going to see the LCR series circuit. When an inductor, capacitor and resistor are connected in series, what will be its impedance, what will be phasor diagram, and also we will solve few numericals. Okay, so watch the video till the end. So without any delay, let's start our class here. So you see here in the diagram, L means inductor, C means capacitor and R means resistor. All three are connected in series and they are connected with an AC source which is having a same frequency and the same current is passing through all these elements, right? I current is passing through inductor, capacitor and resistor. So in my previous class we have seen what will be the phasor diagram for a purely inductive circuit, capacitive circuit and resistive circuit. Okay, so in L, when a current passes through an inductor, it has been seen the potential difference is VL, right, which is leading the current. So you see VL I have written in y-axis and I have written in x-axis. This means that the potential difference which is produced at inductor is leading the current, or you can say the current is lagging behind the voltage. This is given by a phasor diagram. So what is a phasor diagram? Phasor diagrams are represented by a rotating vectors of voltage and current which shows what is the phase difference between them. Right? Now the voltage produced at the capacitor is called Vc, right? That is the potential difference and which is lagging behind the current, or you can say the current is leading in case of capacitor. But in case of resistor, it has been seen the phase difference is 0 because both voltage and current they are in same phase, right? They are in same direction. So combining all these three, this one phasor diagram can be drawn where the potential difference across resistor is taken in x-axis. So in y-axis this is VL and this is VC, right? So you see VL is up, VC is down, but we need to draw here the resultant between all these three elements. So we'll consider V is the resultant voltage of VL, VC and VR. In upper direction you see I have written a VL minus VC. This means that this circuit, in this circuit the voltage which is produced across this inductor is more than the voltage produced at the capacitor. So that is VL must be greater than VC. Okay. So if VL is greater than VC in this circuit, then the phasor diagram phi will make a triangle here. You see the resultant is making a triangle or making an angle phi with the horizontal. Horizontal is VR. Right? Now we need to find here in the triangle AOE, in the triangle AOE, V square equals to VL minus VC square plus VR square. Okay, so VL minus VC, we know VL, last day we have seen that is IXL minus IXC whole square plus V square R means IR square. Okay, and here we can write I square Z square, or if we can write here this is square, we can put here square root directly. So you see from here I, if you take I common here, then I will be getting I square here. So XL minus XC, this square remains as it is, and IR square as it is, here IZ, right? Now similarly from this here I will be coming out from the square root, so we will get XL minus XC whole square plus R square, and here we have IZ, I and I got cancelled. So what is our impedance for this LCR circuit? That is XL minus XC whole square plus R square. This equation can also be written as Z equals to root under XL minus XC can be written as omega L minus 1 by omega C whole square plus R square. So this is the impedance, okay, impedance of LCR circuit. So the impedance which we have derived, that was Z equals to root under XL minus XC whole square plus R square, right? Now if we need to find that phase angle, phase angle of this LCR circuit, that is phase angle, that is phase difference is given by tan phi. Tan phi is given by tan theta equals to P by V. So what we have here, P is given here by VL minus VC by VR, right? So VL can be written as IXL minus IXC divided by IZ, or here IR. Okay, so I can be taken common here. What will get here, XL minus XC by IR. I and I will get cancelled, that is XL minus XC by R. This is tan phi. Okay, so what will be the power factor then? Power factor was given by cos phi. Okay, cos phi was given by B by H. What is our B here then? Here B and H, that is V. So IR and V means here IZ. So I and I will get cancelled. So we will get R by J cos phi. Okay, this is the power factor, and the power associated with this series circuit is P equals to IRMS into ERMS cos phi, where cos phi is the power factor. There are few special cases, like you see, this is an LCR circuit, an impedance for LCR circuit. But in case, if you see that in this LCR circuit, suppose C is not there. If C is not there, then it will become LR circuit, right? Then what will be the impedance then? If capacitor is not there, then capacitive reactance will be 0. So it will become ZL. Then we can write it XL square plus R square. You see, if XC is 0, then XL whole square is XL square plus R square. That time it will become inductive impedance. Similarly, if inductor is not there, only capacitor and resistor is there in the circuit, then from this formula only we can get the other two formulas. So XL is 0, that means minus XC whole square is XC square plus R square, right? So this is capacitive impedance, this is inductive impedance, and this is the impedance of LCR circuit. Similarly, tan phi, just now we have seen that was XL minus XC by R. So if it is an RL circuit, then it will become XL by R, because XC will be 0. Okay, so if you know the formula of this one, if you remember this formula, then you can get the other two very easily. This is very important topic, that is resonance in series LCR circuit. What is resonance condition? So we say that LCR circuit is in a resonant condition when the phase angle is 0, right? That means when phi equals to 0, so we say that here the circuit is in resonant condition. And in resonant condition, the reactance, that is inductive reactance and capacitive reactance, both becomes equal, right? So let's see, as I have told, when phi becomes 0, then cos phi will be 1, that means power factor will be 1. So this is the condition for which a resonant condition takes place in series LCR circuit. Now in series LCR circuit, when phi becomes equals to 0, this also means that capacitive reactance is equal to inductive reactance. Then what will be the impedance? So we know for impedance for LCR circuit, that is XL minus XC whole square plus R square. Now if XC equals to XL, if I substitute here, then XL minus XL, this will become 0. So what we will get? We will left out with only R square. So therefore Z will be equals to R. That means the impedance will be equals to the resistance. That time the circuit will behave like a pure resistive circuit, right? So at resonant condition, XL becomes equals to XC, where the impedance becomes equals to resistance. That means whatever the resistance will be there in the circuit, so impedance will be that resistance. And here it has been seen that the power factor becomes 1 as phi is 0. So this condition is called resonant condition. So as per other condition, at resonance condition, the impedance becomes very minimum and it becomes equal to resistor. That means it becomes purely resistive circuit, right? Now as the circuit is in resonance condition, then what will be the resonance frequency? So we will calculate now what will be the resonant frequency. You see, just now I told that in LCR series circuit, phi becomes equals to 0. That means here the angle subtended between the voltage and current is 0, right? So in this condition, when a voltage and current, when they are subtended with 0 degree, that means when they are in same direction, we say that that condition has been set up in series LCR circuit. So resonance condition is set out in only in LCR circuit when inductive reactance becomes equals to capacitive reactance. So if I write here XL and here XC, both will be correct, right? So in resonance condition, XL becomes equals to XC. XL means omega L and XC means here 1 by omega C. Okay, so if I cross multiply, what will get? Omega square equals to 1 by root LC, and this omega can be written as 1 by root under LC. Also omega can be written as 2 pi f, 1 by root under LC, or f equals to 1 by 2 pi root under LC. So this is the resonant frequency. Okay. So I have noted down one question here. A 50 microfarad capacitor, a 30 ohm resistor and a 0.7 Henry inductor are connected in series to an AC supply, which generates an EMF E by E equals to 300 sin 200t. Calculate the peak value of current flowing through the circuit. We have to calculate the peak current, that is I0 we have to calculate. So first we will note down what is given in the question here. You see 50 microfarad capacitor, that means capacitance is given as 50 microfarad. Okay, 50 microfarad can be written as 50 into 10 to the power minus 6 farad. So 1 micro equals to 10 to the power minus 6 farad, right? Similarly, resistor is given, that means resistance is given here 30 ohm and inductor is given 0.7 Henry. So H is the Henry, stands for Henry, and which is the SI unit for inductor, right? 0.7 Henry. Are connected in series to an AC supply which generates an EMF. So E equals to 300 sin 200t. This is given in the question. So this is E equals to E naught. So E naught is how much? 300 volt, right? So peak voltage is given here 300 volt. And here in this place, if you remember, the formula was E equals to E naught sin omega t. So what is omega here? 200. So omega is here, from the equation we get 200, right? Here we have to find I0, right? So to find I0, you see in my previous class I gave one formula, V0 by I0 equals to Z, right? So Z equals to V by I, or Z can also be written as V0 by I0. So we need to find here I0. I0 can be written as V0 by Z. So V0 is given in the question, you see. V0 and E0 both are same here. So what is Z? Z we have to calculate. So Z formula for LCR circuit. So in this circuit we have R also, C also, L also. So this is an LCR circuit. So what is the impedance formula for RLC circuit? XL minus XC whole square plus R square. So separately first we will find XL. XL equals to omega L. Omega was 200 and L is 0.7. That means 7 by 10 will get cancelled. What will get here? 140. Similarly XC. XC means 1 by omega C. So 1 by omega. Omega is 200 and what is C? Capacitor is given 50 microfarad. So 50 microfarad 10 to the power minus 6 will go up, then it will become 10 to the power 6. So here you will be getting 10 to the power 6 and 2 5s are 10. 1, 2, 3, 4. Right? So 10 to the power 4. If I cancel this one, then I will get 10 square. See what I have done here, 2 5s are 10. So 10 is there. Now except 10, 3 zeros are there. So into 3 zeros. So this can be written as 10 to the power 4 in the denominator, right? Now 10 to the power 6 by 10 to the power 4, if you cancel 4, 6 minus 4 is 2. So ohm, here also unit will be ohm. So XC equals to 100. And R already given in the question, that is 30 ohm. Now we will substitute here in the question, that is Z equals to root under XL minus XC, that is XL we have 140 minus we have 100 whole square plus R over here 30, that means 30 square. 140 minus 100, that is 40, that is 40 square we will get here 1600, and here we will get 900, that is 2500, or we will get 50 ohm. Okay, so this is our Z. So once we get the Z here, then it will be very easy to find out this peak current. So V naught by Z equals to I0. I0 is the peak current which we have to find in this question. So V0 is how much here? 300, and Z we got 50. So 0 and 0 got cancelled. 5, 6 and 30, that means 6 ampere. So what is the peak current of this LCR circuit? That is 6 ampere. An alternating EMF applied across the LCR circuit. So an EMF is applied across the three component of this circuit. The peak value of alternating voltage developed across three components. That means these are the potential difference developed across three components, right? So determine the peak value of the applied EMF and the phase difference between applied EMF and current in the circuit. So what we have to calculate here? Peak voltage of the applied EMF. That means what is the peak voltage, right? That one we have to calculate. So to calculate the peak voltage, that is given by V0 equals to VL minus VC whole square plus VR square. This is the formula, right? So we know that in a phasor diagram, which we see that the resultant V, which is between VL and VC and VR, so that was V. So V means here V0. That means when you are asked to find the peak value of the voltage, that means you will be using V0 equals to VL minus VC whole square plus VR square, right? So this was the phasor diagram, if you remember, right? So this is the peak voltage. So this peak voltage, where it is straight here, this peak voltage, that is V0, V is given by this, so V0 VL minus VC, and this is VR, right? So this magnitude is given by the resultant, that which is given by V0 equals to VL minus VC whole square plus VR square. So in the question you see this diagram, L in front of L, what is given? 8 volt. That means VL is given 8 volt, and VC is given 5 volt, and VR is given 4 volt. So substitute here, that is V0 equals to root under VL minus VC, that is 8 minus 5 whole square plus VR is 4 square. So what we will get here? 3 square, that is 9 plus 16, that is root under 25, that is 5 volt. Okay, peak voltage is 5 volt. Next, what we are asked here, phase difference between the applied EMF and current in the circuit. Now phase difference, tan phi. Now we have to check whether L is bigger or C is bigger. That means which reactance is bigger, voltage is bigger. That means L is greater than C, because this potential difference developed across L is 8 volt and across C is 5 volt, right? So here VL is greater than VC, therefore tan phi will be XL minus XC, or VL, XL and XC is not given in the question, so we will use this formula, VL minus VC by VR. So VL minus VC, that is 8 minus 5 divided by 4, that is 3 by 4, or phi equals to tan inverse 3 by 4. This is the answer. Right. So this type of question for the LCR circuit you practice at home, right? And in my next class I will be teaching this quality factor. What is the quality factor? What is the bandwidth? Right. So when you can understand what is the nature of the resonance that is set by the quality factor. So see you soon in my next online class.